Now, in this lecture, we'll find out the radius of the big circle. In the drawing, we have a big triangle. Inside the big triangle, we have two circles and a square. The radius of the small circle is equal to 1 unit. One side of the square is equal to 3 units. And our mission is to find out the radius of the big circle. Okay, so first of all, we will define the vertex here as A, the vertex of the triangle. We define this vertex as B. We define this vertex as C. We define the center of the circle, of the small circle, as O. We define the center of the big circle as P. Define the touching point of the square with the side BC of the triangle is D. And define the point of tendency of side BC in the circle is E. We define the point of tendency of the square with side BC as F. We define the point, the touching point between the square and the circle is point G. We define the touching point of the square with side AC of the triangle as H. We define the point of tendency of tangent AC and the small circle as J. And we define the point of tendency of tangent AC with the big circle as point K. We define the point of tendency of tangent BC with the big circle as L. And we will define the point of tendency of side AD of the square and the circle as point M. We will join points M and O together by a straight line. Point O is the center of the circle. Point M is the point of the small circle itself. Therefore, line segment OM is the radius of the circle that is equal to 1 unit. And we know that the radius OM, it is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees, this angle also equals to 90 degrees. According rule number 1 states that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Likewise, we have here the radius OE that is drawn to point E, that is the point of tendency. Therefore, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. We know that all the angles inside a square are right angles. Therefore, here all the angles in square GHFO will be equal to 90 degrees. BC is one side of triangle ABC, therefore it is absolutely a straight line. So if you focus on the upper side of the straight line BC at point F, the sum of the angles must be equal to 180 degrees according to rule number 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So if this angle equals to 90 degrees, then this angle must be equal also to 90 degrees. In order to complete the sum of the angles on the upper side of BC at point F to 180 degrees, this angle must be equal to 90 degrees. Likewise, if you focus on the upper side of BC at point D, here this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees for the same reason, according to rule number 3. So actually, I found out that inside the small quadrilateral ONDE, we have 1, 2, 3 right angles. Again, inside quadrilateral OMDE, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Okay, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, if we have 3 right angles in a quadrilateral, the fourth angle must be equal to 90 degrees. So inside quadrilateral OMDE, we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral OMDE as a rectangle because it has 4 right angles. I write it down. Quadrilateral OMDE is a rectangle. This quadrilateral is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, MO is equal to DE. MO is equal to DE. But MO equals to 1 unit. It is the radius of the circle. So we can write here that MO equals to 1. And from this equation, 1 equals to MO equals to DE. We derive that DE is also equal to 1 unit. DE is also equal to 1 unit. Okay, you can write here that DE equals to 1 unit. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that MD is equal to OE. MD is equal to OE. According to the rule that the opposite sides of a rectangle are equal to each other, but OE is the radius of the circle that is equal to 1 unit, so we can write here that OE equals to 1. And from this equation, MD equals to OE equals to 1, we derive that MD is also equals to 1 unit. MD is equal to 1 unit. Okay, so you can write down in the drawing that MD is equal to 1 unit. Therefore, actually, we found out that this quadrilateral MODE is a square. All of its sides are equal to 1, therefore it is a square. And here I will present to you rule number 2. According to rule number 2, lengths of two tangents from a common external point to a circle are equal. Repeat again on rule number 2, the lengths of two tangents from a common external point to a circle are equal. So here, from the common external point, point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA is equal to PB. You can implement rule number 2 in our drawing, because in our drawing we have here the common external point, point H. From the common external point, point H, we have two tangents to the small circle, tangent edge J and tangent edge M. And according to rule number 2, edge J is equal to edge M. What is the length of edge M? Edge M equals to edge D minus MD. Again, edge M equals to edge D minus MD. That is to say, edge M equals to edge D, that is 3 units, this is one side of the square, minus MD, that is 1. 3 minus 1 is 2, so edge M is equal to 2. So here we can write down that edge M is equal to 2, and from this equation edge J equals to edge M equals to 2, we will derive that edge J is equal to 2 units. Okay. Likewise, we'll focus on the common external point, point C. From the common external point, point C, we have two tangents to this circle, to the small circle, tangent CJ and tangent CE. And according to rule number 2, they are equal to each other. So that is to say, CJ is equal to EC. Okay, so, and if we define EC as X, so here EC equals to X according to our definition, then from this equation X equals to EC equals to CJ, we will derive that CJ is also equals to X. CJ is equal to X. Okay. Here we join points O and J together by a straight line. Point O is the center of the circle, point J is the point of the circle itself, therefore OJ is the radius of the circle, that is equal to 1. Okay. And there we have the radius OJ that is drawn to the point of tendency, therefore this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees according to rule number 1. In the next step, we will implement the Pythagoras theorem in the right green triangle, triangle edge DC. Okay. So, according to the Pythagoras theorem, here PT is the relation for Pythagoras theorem. The square of the hypotenuse is equal to the sum of the squares of the perpendiculars. The hypotenuse in the green triangle is HC, therefore the square of the hypotenuse is HC squared. and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to HD square plus DC square. Repeat again, according to the Pythagoras theorem, in the right green triangle HDC, HC square equals to HD square plus DC square. So here, the hypotenuse HC is equal to 2 plus x, therefore HC square will be equal to 2 plus x square. And it must be equal to HD square HD equals to 2 plus 1, that is 3. Therefore HD square is 3 squared, that is 9. Plus DC square. DC equals to 1 plus x, therefore DC square equals to 1 plus x square. So, in conclusion, we found out that according to equation number 1, two plus x squared equals to 9 plus 1 plus x squared. Here we'll open the brackets on both sides of equation number 1, and we'll get that according to equation number 1, two plus x squared is equal to 2 squared, that is 4, plus x squared, plus 2 times 2x is 4x, and it is equal to 9 plus 1 plus x squared equals to 1 squared, that is 1, plus x squared plus 2 times x. So here we have x squared on both sides of equation number 1, so x squared will get cancelled. What is left from equation number 1 after we cancelled x squared? What is left is that in this side of the equation we have 4 plus 4x, that is equal to 9 plus 1 is 10 plus 2x. Here we'll subtract from 4 from this equation, equation number 1, and we get that according to equation number 1, 4x equals to 10 minus 4 is 6 plus 2x. So here we subtract 2x from this equation, equation number 1, and we get that according to equation number 1, 4x minus 2x is 2x, and so 2x equals to 6. 2x equals to 6. Here we divide this equation, equation number 1 by 2, and we get that x equals to 6 over 2, that is 3. So we found out that x equals to 3 units. We can write down here that x equals to 3 units. X equals to 3 units. Okay. In the next step, we'll join point C and O together by a straight line. By joining point C and O by a straight line, we created here two green right triangles. We'll put the two small green right triangles can go into each other according to side rule. So we'll focus on triangle JCO and the small green triangle OEC. So why those two small green triangles can go into each other? First of all, we just right now found out that CE is equals to CJ, and they are both equal to 3 units, and this is according to rule number 2. Okay. In addition, EO or OE is equal to OJ, and they are both the area of the circle that is equal to 1 unit. And finally, CO equals to itself. OC equals to OC. It's a common side that belongs to both triangles. So we actually found out that the two green right triangles can go into each other according to side rule. So I write it down. Triangle OJC can go into triangle OEC according to side rule. Okay. So if we define this angle as theta, then this angle must be also equal to theta because of the fact that they are equal to each other. In the next step, we will join points J and D together by a straight line. So actually, line segment OC, this line segment OC is the angle bisector of angle C. I want it again. Line segment OC is the angle bisector of angle C. I write it down. Line segment OC is an angle bisector of angle C actually it divides angle C into two halves, each half equals to theta, and it is the angle bisector of angle C in triangle JDC, triangle JDC. Oh, okay, so triangle JDC. Repeat again, OC is angle bisector of angle C in triangle JDC. So here we will join points C and P by a straight line. We will join points P and K by a straight line. So here, point P is the center of the circle, of the big circle, point K is the point of the big circle itself, therefore PK is the radius of the circle that is equal to capital R. In the next step, we'll prove that the big right triangle, actually here, we have the radius PL that is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Likewise, we have the radius PK that is drawn to the point of tendency, therefore this angle will be also equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So, in the next step, we will prove that the right big triangle PKC is congruent to the right big triangle PLC. They congruent to each other according to side rule, and we'll prove it now. First of all, write those two triangles congruent to each other. First of all, PK equals to PL, they are both the radii of the big circle that is equal to R. PK equals to PL, they are both equal to R. In addition, if we focus on the common external point C, from the common external point C, we have two tangents to the big circle, tangent PK and tangent CL, and according to rule number 2, the two tangents are equal to each other, that is to say, CK equals to CL. CK equals to CL according to rule number 2. And finally, PC is a common side that belongs to both triangles, so you can write down that PC equals to itself. PC equals to PC is a common side that belongs to both triangles. So we actually proved that the two big right triangles can go into each other according to side rule. I write it down. The big right triangle, triangle PKC, is congruent to the big right triangle, triangle PLC, according to side rule. And from the fact that those two right big triangles can go into each other, we will derive that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. The two big right triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if we define one angle as theta, then the other angle must be also equal to theta because of the fact that those two angles are equal to each other. In the next step, we will join points K and L together by a straight line. This way we created here triangle LKC. So actually we found out that PC, side PC or segment line PC, is the angle bisector of angle C. I write it down. PC is the angle bisector of angle C. It bisects angle C into two halves, each half equals to theta. In triangle LKC. So, I'll repeat again. Here, PC is the angle bisector of angle C in triangle LPC. So you can see here, PC bisects angle C into two halves, each half equals to theta, and it is in triangle LKC, the big triangle, triangle LKC. So angle C is two angle bisectors. The first angle bisector is OC and the second is PC. Okay. So here we have here a claim that the angle bisector CO passes through point P. Again, our claim is that the angle bisector CO passes through point P, or in other words, points P and point C, O and P, they are all located on the same straight line. So I write down our claim. Our claim is that the angle bisector CO, this angle bisector, passes through point P. I repeat again on our plane. Our claim is that the angle with respect to CO passes through point P. Okay, so we'll prove the claim in a negative way. Okay, so in a negative way, let's assume that CO doesn't pass through point P. So our assumption is that CO doesn't pass through point P in a negative way. So if CO doesn't pass through point P, it means that we will have here two angles. The first angle is angle DCO. This is angle DCO, that is equal to theta. So here I draw the first angle that we have here. Angle, actually it is angle OCD. And angle OCD is equal to theta. So this is the first angle that we have, that is angle OCD, that is equal to theta. And the second angle is angle PCB. Angle PCB. The second angle is angle PCB. Again, this is the second angle that we have, that is angle PCB. This is angle PCB. And here, according to our assumption, first of all, it is very easy to see that DC is part of BC. Again, DC is part of BC. So if DC is part of BC, it means that they are both located on the same straight line. Okay, so we can write down that the first leg of the two angles are located on the first legs of those two angles. They are located on the same straight line. In DC and BC, they are both located on the same straight line because of the fact that DC is part of BC. Okay, DC and BC, they are both located on the same straight line, while the second leg of those two angles, it is OC and PC. What is about OC and PC? This is leg OC and this is leg PC. According to our assumption, OC doesn't pass for point P. If OC doesn't pass for point P, it means that point C, O, and P, they don't located on the same straight line. If OC doesn't pass for point C, it means that OC and PC, they are located on two different straight lines. Okay, so we can write down that the second leg, that is OC and PC, according to our assumption that OC doesn't pass for point P, are not located on the same straight line. Okay, CO and CP, they are not located on the same straight line. Why? Because CO doesn't pass for point P. So if we have two angles, that one angle of those two angles, that one leg is located on the same straight line, in order that the two angles will be equal to each other, the second leg must be also located on the same straight line. Otherwise, the two angles will never be equal to each other. Okay? So, I will write it down that in order that the two angles will be equal to each other, the second leg the second leg of the two angles, that is to say CO and CP, must be also located on the same straight line. But according to our assumption that CO doesn't pass for point P, then the second leg of the two angles, the second legs of the two angles that are CO and CP doesn't located on the same straight line because CO doesn't pass for point P. Therefore, angle OCP doesn't equal to angle PCB. So here the second leg of the two angles, of the second legs of the two angles must be also located on the same straight line, but according to our assumption that CO doesn't pass for point C, it doesn't. Therefore, angle OCP is not equal to angle PCB. Okay? So here, if angle OCD is equal to theta, then angle PCB will not be equal to theta but to alpha. Okay? So we actually found out that according to our assumption, we actually found out that angle C has two different angle bisectors. That is to say OC and PC, that bisected into two different arms to theta and theta and alpha and alpha, and alpha doesn't equal to theta. And it is impossible. Why? Because it is impossible because if angle C equals to 30 degrees, then any angle bisector of angle C will bisect it into 15 degrees and 15 degrees only, and not to any other halves. Not to any other halves. Therefore, so due to our assumption in a negative way, we arrived to a contradiction. Therefore, we must conclude that our assumption is not correct. Therefore, our assumption that OC doesn't pass for point P is not correct. Therefore, we must conclude from it that OC passes for point P. Okay? Due to our assumption that CO doesn't pass for point P, we arrive to a contradiction. Therefore, our assumption is not correct. Therefore, CO passes for point P. Okay? So, in the next step, we'll focus on the right small triangle ODC, triangle O. We'll focus on the small right triangle OEC, and we'll define this angle. So this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus theta. Okay? Why? Because 90 degrees minus theta plus theta equals to 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. In the next step, we will focus on the right big triangle PLC. On the right big triangle PLC, this angle equals to theta. This angle equals to 90 degrees. Therefore, this angle must be equal to 90 degrees minus theta. Okay? So, in the next step, we will prove that the right big triangle PLC is similar to the right small green triangle OEC. Okay? So, the right triangle PLC is similar to the green small right triangle OEC. So why those two right triangles are similar to each other? So first of all, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So I can write down that this angle, that is actually angle EOC, or this angle, that is angle LPC, the big right triangle, is equal to this angle, that is actually angle EOC. Okay. Repeat again, angle L, angle LPC, angle LPC is equal to angle EOC, they are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So this angle, that is actually angle PLC, is equal to this angle, that is actually angle OEC. Repeat again, angle PLC is equal to angle EOC, they are both equal to 90 degrees, therefore they are equal to each other. And finally, this angle, angle theta, is a common angle that belongs to both triangles, so we can write down that angle theta equals to itself. So we can define angle theta as angle PCL that is equal to angle theta itself, that we can define angle theta also as angle OCE. Repeat again, angle theta equals to itself. It's a common angle that belongs to both triangles. So actually we found out that the big right triangle, triangle PLC, can go into the small right triangle, triangle OEC, OEC according to angle similarity rule. So here, the big right triangle, triangle PLC is similar. This is the sign of similar to the right small green triangle, triangle OEC, according to angle similarity rule. And for the fact that the two right triangles are similar to each other, we derive that the following relationship exists between their sides. We conclude that PL in the big right triangle over OE in the small right triangle is equal to LC in the big right triangle over EC in the small green right triangle. Repeat again. We conclude that PL over OE equals to LC over EC. PL is the radius of the big circle that is equal to R over OE. OE is the radius of the small circle that is equal to 1. And it is equal to LC. What is the length of LC? LC equals to 3 plus 1 plus 3, that is 7, plus LF. Again, LC equals to 7 plus LF over EC. EC equals to 3 units. So in conclusion, according to equation number 1, R equals to 7 plus LF over 3. We will multiply this equation number 1 by 3. And we get that according to equation number 1, R equals to LF plus 7. Here we subtract 7 from this equation number 1, and we get that according to equation number 1, LF equals to 3R minus 7. LF equals to 3R minus 7. Here LF equals to 3R minus 7. So we know that one side of square GHFD equals to 3 units, and the value of the length of the radius of the big circle, the radius that we are looking for, could be less than 3 units, it could be equal to 3 units, and the radius could be also greater than 3 units. So we'll examine the 3 cases in order to find out which case is true, is correct for our drawing. So we'll examine the first case, that so it is case one, that R, the radius of the big circle, is less than 3 units. So if R is less than 3 units. Okay, the first case is R is less than 3 units. So actually we have a circle, then the radius of the circle is less than 3 units. So the radius, this radius, R is less than 3 units. This is also the radius R that is less than 3 units. And we know that one side of a square is equal to 3 units, so the side of the square will be little bit higher than R, because R is less than 3 units. So we have here quadrangle PGLF. Inside this quadrangle we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So inside quadrangle PGLF we have 4 right angles, therefore we will relate to quadrangle PGLF as a rectangle. Why? Because it has 4 right angles. Quadrangle PGLF is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, side PG of the rectangle is equal to side LF. but PG equals to R. So we can write here that PG equals to R, and from this equation R equals to PG equals to LF, we will derive that LF is also equals to R. Likewise, we know that PL equals to GF. According to the rule that the opposite sides of a rectangle are equal to each other, PL equals to GF. But PL equals to R, it is the radius of the circle, and from this equation R equals to PL equals to R equals to PL equals to GF, we derive that GF is also equals to R. So we actually found out that for the other P, G, and F, it is not a rectangle, but it is a square, because all of its sides are equal to R. From one side, LF equals to R. From the other side, we have already found out that LF equals to 3R minus 7. Okay, so in conclusion, we found out that 3R minus 7 equals to LF equals to R. And from this equation, we will derive that 3R minus 7 is equal to R. Here, we subtract R from this equation and we get that 3R minus R is 2R, so 2R minus 7 equals to 0. We'll add 7 to this equation and we'll get that 2R equals to 7. We'll divide this equation by 2 and we'll get that R equals to 7 over 2 is 3.5. So we found out that the radius of the circle is equal to 3.5, while according to our assumption R is less than 3 units. So we have a contradiction. R cannot be equal simultaneously to 3.5 and less than 3 units. So there is a contradiction, and therefore, due to the contradiction, we derive that R cannot, the radius of the circle R cannot be less than 3 units, because otherwise we will have a contradiction. Okay, so we'll examine the second case, that R is equals to 3 units. So case 2 is that R is equals to 3 units exactly. Okay, R equals to 3 units. So if R equals to 3 units, then we will have a circle with a radius of 3 units. So the radius of this circle is equal to 3 units, so R equals to 3. And one side of the square is also equals to 3 units. So in quadrilateral PGLF, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So quadrilateral PGLF has 4 right angles, therefore quadrilateral PGLF is a rectangle. Because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, PG is equal to LF. PG is equal to LF, but PG equals to 3 units. This is the radius of the circle. So from this equation, 3 equals to PG equals to LF, we derive that LF is also equals to 3 units. LF equals to 3 units. Likewise, we know that PL is equal to GF according to the rule that the opposite sides of a rectangle are equal to each other. Okay, so here GF is equal to 3 units because it is one side of the square. So actually, we found out that LF equals to 3 units from one side, but from the other side we have already found out that LF equals to 3R minus 7. And from this equation 3 equals to LF equals to 3R minus 7, we derive that 3 equals to 3R minus 7. We will add 7 to this equation and we will get that 10 equals to 3R. We divide this equation by 3 and we get that R equals to 3 and a third. R equals to 3 and a third. But according to our assumption, R equals to 3 units. So we have here a contradiction. R cannot be both equals to 3 units and to 3 and a third. So due to the contradiction, we conclude that R cannot be equal to 3 units. So we left with the third case, that R is greater than 3 units. So case 3 is that R is greater than 3 units. So if R is greater than 3 units, then we have here a circle that its radius is greater than 3 units. While one side of the square is equal to 3 units. So here the side of the square will be shorter than the radius. So here from point H, this point will go perpendicular on the radius PL. So this angle equals to 90 degrees. And this angle will be equal to 90 degrees. According to our construction, we will define the touching point of the perpendicular from point H and PL as T. So inside quadrilateral THLF, we have 1, 2, 3 right angles. Again, inside quadrilateral THLF, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So quadrilateral THLF has 4 right angles, therefore quadrilateral THLF is a rectangle. Quadrilateral THLF is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, TL is equal to edge F, but edge F equals to 3. And from this equation, TH equals to edge F equals to 3, we derive that TL is also equals to 3. TL equals to 3. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we conclude here TH, we get that TH is equal to LF. Side TH equals to LF. But we have already found out that LF equals to 3R minus 7. So we can write here that LF equals to 3R minus 7. And from this equation, TH equals to LF equals to 3R minus 7, we derive that TH is also equals to 3R minus 7. TH is equals to 3R minus 7. And what is the value of TP? The value of TP, it is very easy to see from the drawing that TP is equals to PL minus TL. Again, PT or TP is equals to PL minus TL. So TP is equal to PL, that is the radius of the circle, minus TL, that is equal to 3. So in total, we found out that TP equals to R minus 3. R minus 3, and we already found out that TH equals to 3R minus 7. In the next step, we join points P and H together by a straight line. Point P is the center of the circle, point H is the point of the circle itself, therefore PT, this is exactly the definition of a radius, therefore PH is the radius of the circle that is equal to R. In the next step, we will implement the Pythagoras theorem on the right green triangle, triangle PTH. So I will copy the right triangle, triangle PTH in a new page, and we will implement the Pythagoras theorem on the right green triangle, triangle PTH. So this is the right triangle PTH that I copied from the original drawing. We'll implement the Pythagoras theorem on this right triangle. So here I write it down that by PT, information for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is pH, therefore the square of the hypotenuse is pH squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to PT squared plus TH squared. Repeat again. In the right triangle PTH, according to the Pythagoras theorem, we get that pH squared equals to PT squared plus TH squared. Okay, so pH is equal to R, therefore pH squared is R squared. That is equal to PT squared. PT is R minus 3, therefore PT squared is R minus 3 squared plus TH squared. TH equals to 3R minus 7, therefore TH squared equals to 3R minus 7 squared. So here we'll open the brackets on both sides of the equation. And we'll open the brackets on this side of equation number 1, and we'll get that according to equation number 1, R squared equals to R minus 3 squared equals to R squared plus 3 squared, that is 9, minus 2 times R times 3 is minus 6R, plus 3 minus R squared equals to 3R minus 7 squared equals to 3R squared, that is 9R squared, plus 7 squared, that is 49, minus 2 times 3 is minus 2 times 3 is minus 6, and minus 6 times 7 is minus 42, so in total this expression will be equal to minus 42R. Okay, so here we have R squared on both sides of the equation, so R squared will get cancelled. So what is left from equation number 1 after we cancelled R squared? In this side of the equation, nothing is left. We have 0. That is equal to, here we have 9 plus 49 is 58. And we have minus 6R minus 42R is minus 48R plus 9R squared. So actually we have here a quadratic equation that states that 9R squared minus 48R plus 58 is equal to 0. The general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we will find out the value of x using the following formula, that x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, a is equal to 9, b is equal to minus 48, and C equals to 58. And the variable that we are looking for is R, so X equals to R. We substitute X by R. So we'll put the values of the data inside the equation for X, and we'll find out that X equals to R, so R is equals to minus B. B equals to minus 48, therefore minus B is minus 48, that is 48, plus minus square root of B square is B is minus 48, so the square root of B square is minus 48 square, that is 2,304 minus 4 times A is minus 4 times 6 is minus 36, and minus 36 times 58 is 2088. All divided by 2A. A is 9, so 2A is 2 times 9, that is 18. So here we get that R equals to 48 plus minus 2304 minus 2088 is 216, so inside the root we left only with 216 over 18. So here we actually found out that the radius that we are looking for is equals to 48 plus minus the square root of 216 is 14.6969 over 18. So here R equals to 48. We have two solutions for R. The first solution is R equals to 48 minus 14.6969 over 18. 48 minus 14.6969 is 33.3031 over 18. 33.303 over 18 is 1.85. So I found out that the radius of the circle, of the big circle, is equal to 1.85 units. That is less than 3 units. But we have already found out that R cannot be less than 3 units. Therefore, this solution is incorrect solution. We'll cancel this solution and we'll focus on the second solution, that R equals to 48 plus 14.6969 over 18. 48 plus 14.6969 is 62.6969 over 18, and 62.6969 over 18 is equals to 3.483 units. So I found out that the radius of the big circle equals to 3.483 units, that is bigger than 3 units. Therefore, the solution is correct solution because R is greater than 3 units, and according to our analysis, we have already found out that R can be greater than 3 units. So I finished with the question. In the next step, I will summarize the lecture. I repeat, on the question, in the drawing, we have a big triangle. Inside the big triangle, we have two circles and a square. The radius of the small circle is equal to 1 unit. One side of the square is equal to 3 units, and our mission is to find out the radius of the big circle. Okay, so we actually used 3 rules in order to solve the question. The first rule was that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here we have tangent AB, that is tangent to this circle is at point M. Point M is the point of tendency. And we have the radius OM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. Therefore, this angle equals to 90 degrees, and this angle equals to 90 degrees, according to rule number 1. Then, I presented to you rule number 2, that the lengths of two tangents from a common external point to a circle are equal. Here, from the common external point, point P, we have two tangents to this circle, tangent PA and tangent PV. And according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, PA is equal to PB. Okay? Then I presented to you rule number 3, that according to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So if you focus on the upper side of the straight line CD at point O, which angles we have here? We have angle alpha and angle beta, and the sum of those two angles is equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. So we use those 3 rules in order to solve the question. And here we arrived to this drawing by using the 3 rules. And then we have here a quadrilateral OMDE. The small quadrilateral has 4 right angles, therefore it is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, MO equals to DE. MO equals to DE. But MO equals to 1. It is the radius of the circle. So from this equation, 1 equals to MO equals to DE. We derive that DE is also equals to 1. Likewise, in quadrilateral OMDE, OM must be equal to OE according to the same rule, but OE equals to 1. So from this equation, MO equals to OE equals to 1, we derive that MD is equal to 1. So found out that quadrilateral OMDE is a square. Then we used rule number 2 in order to find out that those two sides are equal to each other. That is to say, JC equals to EC. We used rule number 2 in order to find out that AG equals to AM equals to 2 units. Then we implemented the Pythagoras theorem on the green right triangle. According to the Pythagoras theorem on the green right triangle, triangle edge CD, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC edge C square equals to edge D square plus DC square. Edge C equals to 2 plus x, therefore edge C square equals to 2 plus x square, plus edge D square. Edge D equals to 3, so edge D square is 3 square, that is 9, plus OC square. OC equals to 1 plus x, therefore OC square equals to 1 plus x square. Okay, so we actually solved this equation and found out that x equals to 3. Okay, so then we actually proved that those two right small triangles can void to each other according to side rule. Then we joined points J and D together by a straight line, and for the fact that those two triangles can go into each other, we derive that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if one angle is equal to theta, then the other angle must be equal to theta because of the fact that they are equal to each other. So actually I found out here that OC is the angle bisector of angle C in triangle JDC. Then we joined points C and P together by a straight line, and we proved that those two big right triangles can go into each other according to the same rule, side rule, and from the fact that those two right triangles can go into each other, we concluded that those two angles are equal to each other. So if one angle equals to theta, then the other angle must be also equal to theta. Then we joined points L and K together by a straight line, so we actually found out that PC is the angle bisector of the same angle, angle C. So angle C has two angle bisectors, OC and PC. Then we have the claim that OC passes for point P. Okay, our claim is that OC, angle bisector CO, passes for point P, or points P, CO, point C, O, and P, they are located on the same straight line. We put our claim in a negative way. We assumed that CO doesn't pass for point P. In this way, we actually have here two angles, angle OCD that is equal to theta, and the second angle, angle PCB. Because of the fact that DC is part of BC, here DC is part of BC, it means that DC and BC are located on the same straight line. So one leg of those two triangles are located on the same straight line. So in order that the two angles will be equal to each other, the same leg of the angles must be also located on the same straight line. That is to say, OC must be located on the same straight line of PC. But according to our assumption that CO doesn't pass for point P, it means that CO is not located on the same straight line as PC. And because of the fact that CO doesn't located on the same straight line of PC, it means that the second leg of the two angles are not located on the same straight line, therefore they can never be equal to each other. Because one leg is located on the same straight line, therefore the second leg must be also located on the same straight line if we want the two angles will be equal to each other. But according to our assumption, the second leg doesn't located on the same straight line because CO doesn't pass for point P. Therefore, those two angles can never be equal to each other, so if this angle equals to theta, this angle will be equal to alpha. So actually found out that DC, that we actually found out that angle C has two different angle bisectors that are OC and PC, and they bisect angle C into two different halves. While angle bisector OC bisects angle C into theta and theta, angle bisector PC bisects angle C into alpha and alpha, and it is impossible. Why? Because if, for example, angle C is equal to 30 degrees, then any angle bisector will bisect it into 15 degrees and 15 degrees, and not any other halves. So due to the contradiction, we actually concluded that our assumption that CO doesn't passes from point P is incorrect. Therefore, we conclude that CO must pass from point P. Then this we focus on triangle OEC. Triangle OEC, the green triangle, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta, because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, the sum of the angles in any triangle. Likewise, in the right triangle PLC, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. Then we proved that those two triangles can move to each other according to side rule. Those two angles are both equal to 90 degrees minus theta, those two angles are both equal to 90 degrees, and angle theta is a common angle. And from the fact that the two right triangles are similar to each other, we will derive that PL over OE equals to LC over EC. PL equals to R, OE equals to 1, LC equals to 7 plus LF, and EC equals to 3. So we found out that LF equals to 3R minus 7. LF equals to 3R minus 7. Then we actually have three possibilities for the value of R. R, the values that we are looking for, can be less than 3 units, R can be equal to 3 units, and R can be greater than 3 units. We examined each possibility. If R is less than 3 units, then we get here this drawing, and in this drawing we have actually a quadrilateral PGLF is a rectangle, and the opposite sides of a rectangle are equal to each other. So PG equals to LF. Therefore, if PG equals to R, then it means that LF is also equals to R. So from one side, LF equals to R. From the other side, we have already found out that LF equals to 3R minus 7. Therefore, we derive from it that R equals to 3R minus 7. We solve this equation and found out that R equals to 3.5 units. According to our assumption, R is less than 3 units. But here we found out that R is equal to 3.5 units. So we have a contradiction. Due to the contradiction, we must conclude that R cannot be less than 3 units. Then we examined the second case, that R is equal to exactly to 3 units. So if R is equal to 3 units, then we will have this drawing. Actually, quadrilateral PGLF is a rectangle. Why? Because we have here 1, 2, 3 right angles. Any quadrilateral that is 3 right angles, the fourth angle must be also equal to 90 degrees. So this quadrilateral has 4 right angles, therefore it is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, PG equals to LF. But PG equals to 3, therefore LF is also equals to 3. Likewise, PL equals to GF, but PL equals to 3, therefore LF must be also equals to 3. It is equal to 3 anyway, because it is one side of the square. So from one side, LF equals to 3. From the other side, LF equals to 3R minus 7. So from this equation, we get that 3 equals to 3R minus 7. We solved this equation and found out that R equals to 3 and the third. From one side, R equals to 3 and the third, but from the other side, according to our assumption, R equals to 3. So we have here a contradiction. Due to the contradiction, we will conclude that R cannot be equal to 3 units. Then we have the third possibility, the third case, that R is greater than 3 units. If R is greater than 3 units, then we get this drawing. So here r is greater than 3 units, and the square, each side of the square is equal to 3 units. Therefore, here the square is shorter than the radius. And here we have in quadrangle TH, actually from point H we draw perpendicular on the radius PL. Again, from point H we draw perpendicular on the radius PL. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. So inside quadrangle THLF we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. Therefore quadrangle THLF has 4 right angles. Therefore quadrangle THLF is a rectangle, and the opposite sides of a rectangle are equal to each other. So that is to say TH is equal to LF. TH equals to LF, but according to what we already found out, that LF equals to 3r minus 7. And from this equation, TH equals to LF equals to 3r minus 7, we will derive that TH is equal to 3r minus 7. Okay, likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that edge F equals to TL. Edge F equals to TL. TH equals to edge F equals to TL, but edge F equals to 3, therefore TL will be also equal to 3. Okay, TL equals to edge F equals to 3, so from this equation we will derive that TL is also equals to 3. So what is the length of PT? PT is equals to PL minus TL. PT equals to PL minus TL. PL is R, TL is 3, so in conclusion we found out that PT equals to R minus 3, TH equals to 3R minus 7. We join points P and H together by a straight line. Point P is the center of the circle, point H is the point of the circle itself, therefore PT is the radius of the circle that is equal to R. Then we implemented the Pythagoras theorem on the right green triangle, triangle PTH. On the right green triangle, triangle PTH, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say PH square equals to PT square plus TH square. PH equals to R, therefore PH square is R square. PT equals to R minus 3, therefore PT square is R minus 3 square. And TH equals to 3R minus 7, therefore TH square equals to 3R minus 7 square. So according to equation number 1, we found out that R square equals to R minus 3 square minus 3R minus 7 square. We solved this quadratic equation. We got to 2 results for R. The first result for R is that R equals to 1.85 units. But we have already found out that R cannot be less than 3 units. And 1.85 is less than 3 units. Therefore, we will cancel this solution. And we're left only with the second solution. That the radius of the big circle, the radius of this big circle that we are looking for, is equals to 3.483 units. So here the radius is greater than 3 units, therefore it is, according to our analysis, it is a correct answer. So in conclusion, we found out that the radius of this big circle is equal to 3.483 units. And that is the answer to the question. Okay, thank you very much.